with Saeed in the Maths Fundamentals, but we'll go through it again now. We mainly meet it as a proof technique, a way of proving things about the integers. So this is this, on the previous page, this useful phrasing of the induction principle. It's a proof technique. And it's a way of proving a collection of statements, P of n. So this P of n here is a statement, something that's true or false, a statement indexed by the integer n. We'll quickly see some examples. And what we're interested in doing is proving that P of n is true for every integer value of n after some base case. Typically, the base case might be, the starting case might be 0 or 1, or more generally, it could be any particular number. But induction is a way of proving that a collection of statements indexed by the integers are true beyond some point. Okay? And we do it in two steps. We firstly prove somehow that the beginning statement is true, typically that P of 1 is true. And we then prove what's called the inductive step, or the induction implication. We prove that it's always true that P of k implies P of k plus 1. And that holds true for every value of the index in the relevant range. Every value of the index beyond, including and beyond the starting value. And if you've done those two steps, the principle of induction says, well, you've proved that P of n is true for every integer. And we can quite easily, we can appreciate why that is a good state of affairs, why that is true, why that's a true principle about the integers. Because if P of 1 is true, and this implication is true, and it's certainly true for k equals 1, then it's also true that P of 1 implies P of 2. So P of 1 is true, P of 2 has to be true. So then we know P of 2 is true. But then look at the implication again. If P of 2 is true, P of 3 is true. So now we know P of 1, P of 2, and P of 3 are true. Then the implication always applies if we proved it. P of 3 is true, P of 4 is true, and so on. Okay? So each statement implies the truth of the one following. If we know the process starts at P of 1, it will continue and go through all the integers, because that's what the integers are. The sequence of elements starting with 1 plus 1 each time, continuing, gives you all the integers. So what are these P of n's? Well, here's a bunch of examples of them in these 7 problems here. We've got 7 statements here. Really, there are 7 infinite families of statements. And the infinite family is, in each case, indexed by the integers greater than or equal to 1. Okay? So this one, here is one such statement. This says when you add up all the, what are we adding here? It's a summation formula. We're adding up all the odd integers, beginning with 1, and all the way up as far as 2n minus 1. If you add all those odd integers, you get n squared. Okay. Really, okay, it looks like one formula, but really it's an infinite set of statements indexed by n. For every value of n, it's saying something slightly different. Okay. So many of these are summation formulae, and then you've got 2 inequalities down there at the end. So we're going to practice proof by induction as a way of establishing the truth of all of these. And induction, it'll continue to occur at crucial places through the number theory. Okay? So let's just launch in, and we'll prove the classic first example that people almost always see when doing proof by induction, and then we'll move on to some of the more involved ones. Okay? So this first one is question 1. So this formula that we're proving is this. We're adding up all the integers j from 1 to n, and this is n over 2 times n plus 1. Okay, so this is what we're trying to prove. So we do an induction proof of this. Induction proof. Sorry. Okay, so we begin by proving the base case. The base case is when n equals 1, as it is for all of these. So you look at this, you look at the statement in the case of n equals 1. Now, typically, there will not be much to prove here. Typically, it will really just come down to just a careful observation. This is what the left-hand side looks like when n is equal to 1. I've just simply replaced the upper summation limit by 1. So what do you get when you add up all the j's, starting at 1 and ending at 1? What do you get?
1.
1. It's just j equals 1. Nice and simple. What do you get on the right-hand side? Well, when n is 1, you've got a half of 1 plus 1, which is, of course, equal to 1. Yeah. So it's just really just a patient, careful observation. This here, from the far left to the far right, is in fact the statement we're trying to prove for the case n equals 1. So we can say the result is true. The result is true for n equals 1. So the base case is true. Okay, that's good. So now, we've completed, if you look at page 4, we've completed that first bullet point. We now have to prove the second bullet point, which is the implication statement. Now, what we're trying to prove here is an implication. We're not trying to prove that P of k is true on its own. We're not trying to prove that P of k plus 1 is true on its own. We can't do that because we don't know what k is. What we're trying to prove is the implication, that P of k implies P of k plus 1. It's the link we're trying to establish. Not P of k on its own, not P of k plus 1 on its own, but this link. So it's this implication we're trying to prove. How do you go about proving an implication? The most straightforward, direct way you go about proving an implication like this is you allow yourself to assume that the left-hand side is true. You make that assumption. You pretend that the left-hand side is true. You make believe that the left-hand side is true. And with that new temporary belief or assumption, you then try and argue that the right-hand side follows from that assumption. Okay? But it's crucial to be aware that that's what we're in the business of doing here. We're not trying to establish P of k on its own. We're not trying to establish P of k plus 1. We're trying to establish the link between them. Now, there are various ways of establishing implications. Sometimes you come at it by a roundabout way using proof by contradiction, or you might prove an equivalent statement like the contrapositive, or you might do various things. But the most straightforward thing is just to make the temporary assumption of the left-hand side and then try and argue your way towards the right-hand side. Okay. So we assume now, we assume that the sum from j equals 1 up to k of j is equal to k over 2 times k plus 1. Now, what is this k? This k is some integer value in the relevant range. We make this assumption for some value of k greater than or equal to 1. So it's important here that this k could be beginning at the base case, or it could be a greater value. And when you're getting used to this, when you're learning proof by induction, getting acquainted like this, it's a good idea to put in lots of explanations and directions for yourself. So just remind yourself what we're going about. We made this assumption. Now we try and derive the formula, the summation formula for n equals k plus 1. So you imagine the statement we're trying to prove, but with k plus 1 in the place of n. You try and prove that. Okay, that's an equation. The most straightforward line of attack against an equation to try and prove it is just to start with the left-hand side and try and work your way to the right-hand side, or vice versa. Okay. So we'll begin with the left-hand side. And by manipulating that, hopefully we will arrive at the right-hand side. Okay. Now, you're going to see me do this a lot. A way of guiding yourself in constructing proofs. This is where the argument happens then, here. Doing an argument like this, it's a bit like setting out on a journey, on a walk, a logical, mathematical walk. You need to know where you're going, or that helps. If you know where you're going, that helps make the journey. And in this case, we do know where we go, okay? We know what we want to get on the right-hand side. We want to get this expression here, where n is equal to k plus 1. So we'll put down that endpoint here. So we're going to have k plus 1 over 2, all of it multiplied by k plus 1 plus 1, which will be k plus 2. Okay. So I know that that's the required destination. Okay. And I want to show that this is equal to this. Okay. So I just need to use, so what kind of things am I going to use here? I'm going to use a combination of axioms 1 to 10, meaning just regular symbolic manipulation of integers. I can multiply things out, I can factor things, I can add and subtract things in the normal manipulation techniques. And one other crucial tool is this assumption. Okay. I'm not trying to magic up the formula out of nothing. Okay. That's too much to ask for. I'm not trying to prove it on its own. I'm trying to show that it follows from this assumption. So I want to use this assumption in the course of this argument. Everybody with me so far? Yeah? I'm trying to approach this very carefully and set it out. Now, in what way can we use this assumption? At the moment, I've got a summation expression here. I want to arrive at some kind of polynomial in K. It's a quadratic polynomial. K squareds, Ks, and constants here, if you multiply that out. The assumption I've got tells me how to move from a summation to a quadratic in K. So it's a very good tool, isn't it? In broad terms, I want to go from a summation of J to a quadratic in K. Well, that's exactly what the summation does, in a slightly altered way, but it goes from a summation of J to a quadratic in K. So I do really want to use this assumption. But how can I use it? Well, if you look at these two left-hand sides, they're almost the same. Not quite. This is a summation of all the j's from 1 to k. This is a summation of all the j's from 1 to k plus 1. One little step further. Yeah. So I can emphasize that, or I can draw that out by saying within this summation, you will find this summation, which is exactly this one, adding all the j's from 1 to k plus 1. Well, within that, there's adding all the j's from 1 to k. But to correct it, to complete the equation, separately, we add on the last value of j, the value of j that's been omitted from this summation, which is the value k plus 1, okay, the last value of j. So the justification for what I've done there is just an algebraic manipulation, just manipulating the summation notation, really. Can everybody see that? Is there any clarification I can offer on that? Look at what the summation instruction is saying. This says add all the j's beginning at j plus 1 through j plus 2, j plus 3, until you hit j equal to k plus 1. That says almost the same thing, except it stops at one point earlier. Yeah. The remaining thing to do is to add on the last value of j, meaning k plus 1. The reason I did it like that and didn't separate it any other way is because this is exactly what appears in my assumption. So I can now use the assumption by a simple replacement, simple substitution, if you like. So this I can replace by k over 2 into k plus 1. And I've still got this k plus 1. So the crucial justification there is this is from the assumption. Which assumption? Well, I just made one assumption a few sentences earlier, so it's clear. Yeah. Am I on the right track? Are we on the right track? Are we making progress towards our destination? We're trying to get to a quadratic in K. What's this? It's a quadratic in K, some kind of a quadratic in K. Probably, hopefully, they're the same. Could we just step back and declare that they're the same? Would you believe me if I just said they're the same? Maybe not. Maybe there's a bit of convincing we can do. We should do some kind of manipulation or persuasion that this is nevertheless equal to that. Okay, what are we going to do? Well, I mean, one thing we spot is a common factor here, k plus 1, in these two terms. And there is a factor of k plus 1 here. Or more specifically, a factor of k plus 1 over 2. And in fact, I see here a k plus 1 over 2. So, yeah, we're going to factorize this. It's k plus 1 over 2. So I extract out this factor from what I've got here. So what's left behind? Well, when I take k plus 1 over 2 away from the first term, when I factor it out, what remains behind is k. Excuse me. Yeah. What's left behind here? 2. Yeah, because I took out the k plus 1, so that would leave behind a 1. But I also took out a 2. When you take a 2 out of 1, what's left behind? Sorry, when you take a half out of 1, what's left behind is 2. Because 1 is really 2 halves. So when you factor out the half, what's left behind is the 2. So somehow that convinced you, that explanation, but really I've just written down exactly the same thing that was written there before. So that tells you that, there's a lot of information when we're commenting on these things. You want to somehow get there. So, I mean, what's the justification for saying this is equal to this? Just again, it's just factorization, by factorization. Okay, that's a chain of equations. But if we look at the beginning and end, as exactly as we set it up, what we have there is the formula for n equals k plus 1. This summation equals that quadratic in k. It's exactly the required result for n equals k plus 1. So we were attempting to derive this from the assumption, and we did indeed do that. Okay. So I can say this completes the derivation. These little notes are good. They're good, explains to the reader what's happening. Of course, the reader is you several weeks hence when you're revising and working through this stuff again. The first person you're writing for is yourself, and by extension, everyone else. So we've completed the derivation, then we should do one last thing. We should invoke the principle of induction, just to finish off the argument. So we've done two things. We've established the base case. We've established the implication. So by the principle of induction, we can say the formula is true for all it's implied that these are integers. And when you're in a number theory course, whenever you see n, it will take it to be an integer unless we explicitly state so otherwise. Yes, question like that. Slide it up there, yeah. So by the principle of induction, the formula is true for all n greater than minus 1. So we're just finishing the argument off by just invoking the principle. Okay? It's like casting a spell, or I don't know, ending a prayer. It's just, the thing isn't complete until you've said that. Any questions or clarification or points to make about that? In some ways, that's the easiest one. That's the one that everybody sees first when we look closely at induction. They get a bit more involved. Can I switch that? So which one should we go for now? Well, let's go for 4. Oh my God, you want to go? Okay. Yeah, let's go for 4. Let's not hang around. I like that attitude. Okay, we'll see how we get on with question 4. Now, question 4, the result we're going to prove is from the left to the right. The bit in the middle, you see, if we can prove from the far left to the far right, you'll notice that the right-hand side is just the square of that expression there in number 1. So this is just like a little comment that this thing that is equal to the sum of the cubes is in fact the square of the sum. Okay? So it's interesting that the sum of the cubes is equal to the square of the sum. Something about that. Let's do question 4. Notice the structure. It's a sum of cubes equal to a quartic polynomial, an order 4 polynomial. Remember, summation of integer expressions like this, you should kind of link it to integration, or think of it in terms of integration. Adding up cubes should act in kind of the same way as integrating a cubic function. When you integrate a cubic polynomial, you get a quartic, you get an order 4 polynomial. Integral of j cubed is j4 over 4. J to the power 4 over 4. Yeah. So while it's not exactly that expression here, because we're summing, not integrating, but it still follows that same principle. So the base case, of course, is n equals 1, and there's really nothing to prove. Just basically observing that, yes, the thing is true for n equals 1. Yeah? So the second step is to make the assumption. This little subtle technical point here, I think, in when we say, what's going on when we make this assumption. Of course, making an assumption is a bit of a, you have to be careful when you make assumptions. Careful when you make assumptions about people or about any situation. But here in mathematics, you may potentially run into a lot of problems if you make an assumption that you're not allowed to make. If you make an assumption that never holds, okay? So if we had not already proved the base case, okay? If we had not already proved the base case, we could be on shaky ground in making such an assumption. If we just carelessly say, I'll assume this is true for some k greater than or equal to 1. Because maybe that is never true for any such k. And if this equation isn't true for any k, I shouldn't be allowed to assume it is, and then to go building arguments on that assumption. Because if I assume something that in fact is false, it doesn't matter what kind of crazy arguments I build on top of it or interesting arguments I build on top of it. I won't really, everything is, the validity of everything that follows is destroyed because the thing I started from wasn't true. Okay? But because we have proved the base case, I know that the formula is true for at least k equals 1. So to just weaken my viewpoint slightly and generalize and say, well, I'll just assume it's true for some k, for some particular number k greater than or equal to 1, I know that's a valid assumption to make because it is definitely true for that value of k. Maybe it's the only one, but it is certainly true for that one. So it's an allowable assumption to make because we've already observed the base case is true. That's just a small technical point. If I was reading a mathematical argument that just out of the blue said, well, we'll assume that this is true, and then argues from there, well, my suspicions would be raised. You need to justify your assumptions. But this assumption is justified by the fact it is true for at least one value. Okay. And now we try. Let's be positive about it. Forget the try. Now we derive the next equation, the next value of the formula. So this on the left-hand side goes from j equals 1 up to k plus 1, and we're summing j cubes. The very same approach should work. It worked before, why won't it work again? So j equals 1 up to k, j cubed. This sum is certainly inside this sum. What's the bit I need to finish it off? K plus 1, all cubed. Yeah, not just k plus 1, because we're summing j cubed. So it's k plus 1, all of it cubed. Yeah. So that's just algebraic manipulation of the summation notation. Now it's ready to bring in the assumption, isn't it? Because this here is exactly that left-hand side, so we just replace it by and I've still got the k plus 1 cubed. Agreed? Thank you. Now, I was slightly sloppy here. I didn't, maybe you're thinking, where are we going with this? Because we're up at high order expressions now. There's a number of different manipulations you might do with this. So it's good to keep a focus, keep an eye on where we're going. What I'm trying to get to is this expression here, where n has been replaced by k plus 1. Now, whether I write it physically down on the page or not, but I should at least keep it clear in my mind, in our minds. So I'm expecting to get that expression to be a quarter of the square of k plus 1 times the square of k plus 2. Yeah, where the n has been replaced by k plus 1. So a quarter times the square of k plus 1 times the square of k plus 2. Well, have we got any elements of that here? quarter times the square of k plus 1 times the square of k plus 2. Well, a quarter times the square of k plus 1 is there already. That's good. Part of my expression I need. And there's also a square of k plus 1 in there, isn't there? It's k plus 1 cubed, but within that is a factor of k plus 1 squared. So the manipulation I should do is to factorize that part out. So that's just manipulating sigma. This is from the assumption. So now I'm starting to build up to my required expression on the right-hand side. Okay, the expression I need has this in it, a quarter of the square of k plus 1. So force it out. So what's left behind? Well, what's left behind from the first term is k squared. What's left behind from here when I take
4k plus 4.
4k plus 4, 4k plus 4, indeed. Or let's just write it like this for the time being, 4 times k plus 1. When you extract out the k plus 1 squared, you leave behind k plus 1, so it was k plus 1 cubed, yeah? Taking the square out of the cube. But we also forced out a factor of a quarter. So how do you do that? You have to leave behind a factor of 4 to compensate, yeah? So you can extract a factor of a quarter out of anything as long as you leave behind a factor of 4. Because 4 over 4 is 1. And just a little bit of rewriting there, that's k squared plus 4k plus 4. And what is that? Well, k squared plus 4k plus 4, that factorizes nicely. It is just the square of k plus 2. So quarter k plus 1 squared times the square of k plus 2. And that, from beginning to end there, is exactly the formula when n equals k plus 1, isn't it? Compare it to the formula at the head of the page, replace n with k plus 1, you get exactly this. Okay? So this completes the derivation. So, by the principle of induction, the formula must be true for every value of n. Integer value of n bigger than or equal to 1. Yeah? N being integers is implied. Okay. Does that look okay? Any clarification that you would like or comments to make on that? I'll try propping this door open to get some air moving. Okay, we'll move on to another example shortly, but any comments or questions? I do want to do at least one more because one of the inequality ones. So let's do so the other ones of questions 1 to 5 should work out for you in a similar approach to what we used there. Okay. The approach to any of 1 to 5 should be more or less the same. But things might work slightly differently for the inequality. So let's look at question 7. So this is what we're trying to do. Again, it certainly is a candidate for induction because it's an infinite set of statements indexed by n. What this is doing is giving you an upper bound for the exponential 2 to the power n in terms of the factorials. So 2 to the power n seems to be bounded above by factorial of 2n divided by the square of the factorial of n. Okay? Useful for some things, I'm sure. Combinatorics or counting arguments and so on. Okay, so, well, base case, first of all. So when n equals 1, what do we have? 2 to the 1 is 2. And how does that compare to 2 factorial over 1 factorial by 1 factorial? 2 factorial is 2, 1 factorial is 1, so 2 over 1 is just equal to 2. Okay, but equals is compatible with less than or equals, okay? So the inequality is true for the base case, yeah? The only problem would be if I had a strictly greater than there, then I'd be violating the, okay? But this is compatible with that, so the base case is true. Okay, we know what to do now. We make the assumption. Okay, it's the beauty of these induction proofs. So much of the structure is there for you. Okay. So we assume that 2 to the k is no greater than factorial of 2k times the square of the factorial of k. And we're making this assumption for some value of k in the range greater than or equal to 1. For a value of k in the range k greater than or equal to 1. And we now attempt to get to the next case. So whether you write it down on the page or just imagine it in your mind, the next case of the inequality says 2 to the power k plus 1 is no greater than the factorial of 2k plus 2 divided by the square of the factorial of k plus 1. So now we derive the inequality for n equals k plus 1. Again, until we see the approach fail, we may as well try the direct approach, okay? Where we begin on the left-hand side of the inequality and try and move to the right-hand side, okay? Now to guide me in this, I will put down the required right-hand side here. So it's going to be 2k plus 2 factorial of it. And the square of the factorial of k plus 1. And I got to get from here to here. I haven't put in any equal signs yet because the way I've got to get from this left-hand side to the right-hand side is in a less than or equal to fashion. So that kind of suggests to me that I'm allowed to make two kinds of step at each stage. I can either make an equal step, just pass through an equality. I can also make strictly greater than steps or less than or equal to steps. So I can progress from here to here by going equals or by stepping up, by replacing my expression with something bigger. What I don't want to do is at any stage replace it by something smaller. Yeah, so I'm trying to show that this is smaller than that, So I can keep building this up until I arrive at that. But I don't want to build it up a bit and then decrease it a bit, because I still don't know. Trying to increase it. Yeah, I don't ever want to shrink it, because then I won't know what the relationship is of this to the end thing. If I go up and down along, if I go on a journey and I go up and down, up and down, up and down, we're unsure of how the end point relates to the start point. Whereas if I go on a journey and I only go across and sometimes go up, go across a bit more, then go up again. But if I never step down, then I know that where I end is not lower than where I started. Yeah, that's what we're trying to do. So I should allow myself to go equals or strictly less than as I move along. So I can do this with algebraic manipulation using standard properties of less than on the integers or greater than on the integers, whatever. And crucially, we're going to have to use this assumption along the way. Okay? We're not proving this. We're not proving the inequality for n equals k plus 1 out of nothing. We're proving that it follows from the assumption for n equals k. That's the crucial. So any suggestions for our first step? Can do some algebraic manipulations or some use of the assumption. Any good preparatory steps, preparation steps we might make?
Equal to 2 multiplied by 2 to the k.
Okay. Good suggestion from Aidan there. You take this and you just emphasize the fact that inside this has a factor of exactly that, 2 to the k. So we're drawing that out. It's 2 to the k multiplied by 2. Doesn't really matter where you put the 2, but there. 2 times 2 to the k. Yeah. That is good because it makes it clear how to use the assumption. Okay. I should now say that this is smaller, that is no bigger than 2 times 2 times that. Okay, this certainly looks good. I'm trying to say that this is no bigger than that arrangement of factorials. I'm now looking at an arrangement of factorials. So I've made some progress. It's not exactly the same as this, certainly.
But why did you put the equal sign at the start? Because you said you're not supposed to put equal sign.
No, I said I would allow myself to do 2 types of things along this journey. Either use an equal sign or use a less than or equal to sign. And I can repeat doing those steps. And then I'll know that what I end with is bigger than or equal to where I started. What I mustn't do is use a mixture of less than and greater than. So then I won't know where I am. Yeah? Get the idea? Okay, this thing here nearly looks like this. Agreed? It's a factorial involving 2k over a product of factorials involving k. That's really what this is, a factorial involving 2k over factorials involving kind of k plus 1. They're pretty damn close.
Could I just put the equal sign again? Or no, it would be wrong.
Well, we're going to have to put something because what we're looking at isn't yet the same as this. So, yeah, we're either going to use equals or another less than. This is maybe a case where we just want to be a bit just confident and just force the issue. Let's just look at the denominator. What I want to see is k plus 1 factorial, k plus 1 factorial. I've almost got that here, but I'm missing a couple of factors, aren't I? What factors am I missing from the denominator here that I need to have for this denominator? 2 factors of k plus 1. Yeah? So what I need here, this is what I've got. What I need is an extra factor of 1 over k plus 1 and another extra factor of 1 over k plus 1. Because then I can multiply this one by k factorial, gets k plus 1 factorial. I can multiply that one by k factorial, and I get k plus 1 factorial. But of course, this equation is now broken. It's no longer true. So how do I quickly fix it again? Well, I could rub those out, but I don't want to do that because they're helpful to me. So how do I compensate for the fact that I've divided by k plus 1 twice?
Multiply it by k and k again.
K plus 1. K plus 1, exactly. Multiply by k plus 1 and multiply by k plus 1. Okay, now, full stop, the equation is true, is it not? All I've done is multiplied by 1 in a complicated way. Yeah? K plus 1 over k plus 1 is 1. K plus 1 over k plus 1 is 1. Okay? So on the bottom now, I've got k plus 1 factorial by k plus 1 factorial. Agreed on the denominator?
What happened for k instead?
Well, remember, yeah, so we need to be clear on what the factorials are. Remember, what is k plus 1 factorial? It's k plus 1 multiplied by k minus 1, multiplied by k minus 2, all the way down to 3, 2, 1. Yeah? But of course here, you've got exactly k factorial. Yeah? So the factorial of k plus 1 is just k plus 1 multiplied by k factorial. Yeah? So if you take a k factorial multiplied by k plus 1, you get the factorial of k plus 1. You got to understand that that's how neighboring factorials relate to each other. So that's the manipulation I've done in the denominator position here. K plus 1 times k factorial gives me k plus 1 factorial. And the other copy, k plus 1 times the other k factorial, gives me the other k plus 1. Now that's good, because that's what I need in the denominator. So what have I got left in the numerator? Well, I've got 2k factorial. I've got this 2, and I've got these here. I'll multiply by k plus 1, and I'll multiply this 2 into the other one. Yeah? So what happens now? Any what did you just say? I think you said a crucial thing.
2k plus 1.
Did you use the word magic?
Yes.
You did, yeah. So your comment was we need to magically transform that into, rather than k plus 1, what do we want to see? 2k plus 1. Because if you did see this as 2k plus 1, then by the properties of factorials, got this by 1 less than it by all the other. So this numerator would be exactly the factorial of 2k plus 2. So how does Francesca do her magic? How do you do it?
I don't know, just times the top and the bottom by the opposite. I can't sentence. Yeah, but what a case was not. I don't know.
I mean, are you allowed to magically just write in a 2 there? It's very tempting to do. But everyone first appreciate that if this was a 2 in front of the K, then we'd be finished. Yeah, can everybody see that? Okay, but you're not allowed to just stick in a 2. But what would be the problem if you stuck in a 2? You'd break the equation, wouldn't you? You'd be changing the thing. But I don't have to make this an equation. It has to be less than. So with that in mind, am I allowed just write in a 2? What happens to something if you stick in an extra factor of 2 into the numerator? It gets bigger. If the thing is positive to begin with, you multiply it by 2, it gets a bit bigger. Or you multiply a little bit of it by 2, the thing will get bigger. So yeah, we can. Okay, well, I haven't got enough space to do this here. So what I'm going to do is I'm going to magically put in my 2, and I'm going to change this to a strictly less than. You should write that out on a separate line if you've got space. Okay, so before the red 2, this was equal to this. Yeah? But now we've put in the 2, so it's not equal to what it was, but it's strictly bigger than what it was. Okay? Agreed? But now this expression is equal to this one.
Why do we just have a 2 there? Sorry.
Well, okay, so we were at this point. I think both questions were the same question. We were at this point, agreed? Why did we bring in the k plus 1s? It was to arrange the denominator to be what we wanted it to be. Agreed? Yeah? But you can't just magically put in k plus 1s. You must preserve the equation, perhaps, so you put in the k plus 1s in the numerator position to compensate. Then my denominator is fixed, so ignore the red for the moment. My denominator is fixed. I've got an equation here, and the other factors are k plus 1 and 2k plus 2. Now remember how factorials work. So the thing I'm trying to get is the factorial of 2k plus 2. What is the factorial of 2k plus 2? It's the first number, 2k plus 2, times 1 less than it, 2k plus 1, times 1 less than it, 2k, times 2k minus 1, yada, yada, yada. Now this part here, what's that? That's the factorial of 2k. Agreed? Do you agree with that? Everybody? So if you've got the factorial of 2k, which I do have here, and another factor 2k plus 2, which I did have here, 2 times k plus 1, 2k plus 2. The last thing you need is this extra factor of 2k plus 1, which I almost had. I had a k plus 1. Yeah? So magically, we stick in a 2, which breaks the equation. This, and no longer this an equation, breaks the equality, but it breaks it in a nice way for me. It makes the whole expression bigger. Because what was a k here is now, or what was a k plus 1 is now a 2k plus 1. It's a bigger factor in the numerator, so it's made the whole thing bigger. But that is okay, because so now you've agreed that having changed this, this is now equal to this. And what have I got from beginning to end? Okay, I've got a left-hand side and a right-hand side. How does the left-hand side relate to the final right-hand side? Well, if these were all equal signs all the way down, the left-hand side would be equal to the right-hand but they're not. It's a combination of equals and less than or equals, equals, strictly less than, and so on. So actually the left-hand side relates to the right-hand side by the relation strictly less than. So all of these are summarized by the relation strictly less than. So I've proved that 2 to the k plus 1 is strictly less than this quantity here, okay? Which is compatible, which agrees with the stated result, okay? So actually you can strengthen this stated result. It really is a strictly less than, except for the base case of n equals 1 where it is where both things are the same. But thereafter, because of this extra replacement of a k with a 2k, you've actually made it actually strictly removed. Can you all agree how like a combination of equals, less than equals, and strictly less than, combined together, that just means you've got strictly less than, comparing the left to the right. Okay. Now that inequality didn't come from nowhere, it came from, crucially, the use of the assumption, which happened here. So we should indicate where that's happened. So in this step here, we were using the assumption. Do you see what I mean when I said we should do one of these inequality ones, because they're a bit harder. The reason that they're harder, the reason in a way that establishing an inequality might be harder is because there's more choice along the way. If you're just trying to establish an equation, you're very constricted in the things you're allowed to do at each stage, aren't you? So at each stage, you can only just essentially rewrite the thing you've got in a different way, but it must be equal to it. So you're severely constrained. There's a limited range of things that you might do. So therefore, it's in a way, it's simpler to find the correct rewritings. But when you're allowed to pass through inequalities, that means there's a much wider, like I could have replaced, instead of a 2, I could have written in a 10 there, or 5, or 5,003. There's a whole host of inequality jumps I might have made. Now happens 2 is the correct one, so that the thing takes the required form. So inequalities is a lot more choice and possibility of moves you might make. So that means it's maybe harder to find the correct one. So this completes the derivation. So by induction, the inequality is true for all n greater than or equal to 1. Any further questions on that, or any extra clarification you would like on that one? Okay, well, we've still got a bit of time, so why don't you pick and choose from here. Try and do one of the other ones, maybe one of the other summation formulas, or there's another inequality here. Work together with your neighbors. If you've got any questions or any extra queries, I can help you out. So we can run a bit of a tutorial now. If you've got any questions or any queries, please do ask.
Yeah.
Anybody need any extra information? Anybody in college who got it?
Because
Or the what, sorry?
it's like just
When you say you just do technical ones, what do you mean exactly? Oh, so no, no, the direction of the inequality doesn't say whether you do K minus one. You would do K minus one if you were trying to prove that inequality, if you're trying to prove that it held for every negative integer, then you'd start your base case at say 0. Then you assume it's true for K. But then how do you make a step negative? So K minus. So that would be the next value of the index. But as it's written there, we're trying to prove that the inequality is true for every n of and every n prime. So we're always making the assumption that it's true for any K. And then the one we try to derive from that. The plus one isn't related to the direct inequality, it's related to the fact that we want to prove that we're stepping one step.
Like, you know, when you attempt to go in and which side do all work? It makes sense when you find out. Yes, where I actually know. You can't just. That's why I changed it to. That's why I do that to make it without it.
we didn't do that.
Yeah, those two bits. It makes it just like that. I'll write slowly again. Yeah, I understand like why it is like why it's but I don't understand like why people just shut it
Well, yeah. It's a good way to do it.
Is it because you changed it to an inequality?
Yeah, I mean, if what I was trying to prove was some summation equation, and yet we would never want to break our expression. We always want to have two equations. Yeah. Well, yeah, exactly. Stuff like that, because that hasn't changed. This will be possible. But I are breaking, but breaking it is breaking it bad. It's going to stay the same. We want to change it.
So by breaking it, you always have to change the inequality. Yeah.
But it has to go in a compatible direction to the overall inequality within the established, which is this left-hand side is less than. So we begin at something, we want to make our way to the right-hand side, and along the way, we either keep the values or we decrease the value along the way. Let me know our endpoint, which is what we're trying to do in the end.
Yeah, but it's taking how
If we force the issue by sticking an extra 2, in this case that would be a bad thing to do, and then we force but it's allowable and good to do, but it's good to do because it's range to the requirement. And it's allowed because the way that we're doing is compatible with the overall component.
Well, I actually don't do that.
Yeah, it's strange the way, like you said, oh my God, if only there was a 2. That's exactly the right application. You can do like a 2, and you just need to permit yourself to put the 2. Okay? Just be aware of the inequality.
Like that.
That's one thing.
No, it's just like.
That's already. Yeah.
I can't even get half
Yeah. That's an all of you six. My dad, that's fine. Oh, that's what I haven't gone to see all that with me. Because yeah, literally like one thing I was doing 31 and then he's just told us that. That's why you said yes. I did that. Clearly, I'm correct.
Yeah.
You want more.
It's like, I don't actually check for the answers.
No, I haven't. Well, I was like, I got to the point where I got 30 equal minus 3. And then he was like, alright, we'll call it a day. It's still hot.
I mean, I go like
I like how you walk on the country, just standing in. It's like, You're really good on it.
Oh. Oh, you're right, we do already know it's bigger than this.
Wait, should so you get 3 over 2, like that, when you go.
Not really.
What's that? What have you
Because
got?
I got 3 over 2 plus 2. So I got 1 over 2, no, 3 over 2. Because I'm just multiply 1 plus.
Well, you just keep repeating
You do it like
yourself.
that.
I like being myself.
Yeah, I know, it's just taken out some,
We were gonna try something
You're
called
going to use gas.
Then worry about it.
We didn't
Worry about it.
we didn't think.
No, it's just like questions. Alicia wants to I'm just trying to at least get started.
I'm gonna go 1 plus 1
Yeah.
2 k over 2, and then plus a half plus. Yeah, so I did have at some point 3
Because it is all the three of two.
because when I multiplied it out as a half, 1.5, and I ended up with 1.5 plus 3k over 1, which is what you did there. But then I was like, because,
Ah, okay, yeah.
oh, in fact, can I do it wrong? Because
The case where it's one.
I thought that's 3k over 2.
I feel like it's just.
They should be 3k over 4. Definitely not.
It's around now.
Because technically you can write this thing, yeah, no,
Yeah,
you can
because
write it as
I did that the first time I realized. Oh, this is why I don't like fractions.
I mean, technically, 1 plus half plus k over 2 plus k over 4. I think so.
3 over 4.
So I want to try it again. Well, I'm trying to work it out. This is my working function.
No,
Which one might make sense.
Yeah.
Yeah, I think so. Well, this,
I've just gone completely wrong. Like,
The inequalities are a little bit.
Trying. Yeah.
We will see a rise. Crucial. Not this week. John will be taking towards this week. I'll be taking towards next.
So I guess this is untrue for.
We alternate this section. We alternate towards.
Oh, yeah.
Yes, yeah.
Oh, yeah, because no one was talking to the witness yet, and now it's in the meeting, but I'm
Between now and next.
It's on a triple.
she's like, I'm supposed to talk to and I was like, you don't have to have me, like, you didn't tell me. We should have done that. Oh, it comes, She said that if you do a double question, that gives us options. And
When chaos is catching up to
we'll walk on like her.
No, I'm gonna say, like,
But it-
so you get this k over 2 plus k over 2 plus k over 4.
yeah.
Got it, sorry, yeah, you can pick it, I mean, it's all on Moodle, it's PDF. And just the next time you're in, just call by my office and just, I'll just give you a copy then. That's because, so now you've got, so that's some questions here, okay?
Yeah, we're all trying to do something with number 6.
Good, that's- Okay, show me what you've got.
I have very little.
Oh, you're on to it.
We all split the power of K down.
This is not gonna be.
Oh, okay, they're on the same version. Yeah. I tried approaching it backwards as well as forwards, because I didn't work out.
You did
So
16.
I got it and then realised that
Yeah, so you do the same, make this assumption. You go to the next one. Which is you factorize it. Okay, yeah, he's right with 3 over 2 instead of 1 plus half. That's the same.
yeah, no, it's probably going to be.
Is this greater than or equal to? Yeah, so so you were using this assumption here. So okay, but you've written it out correctly here. So you've got greater than or equal to 1 plus k over 2 times 1 plus a half. Because here you don't have this. Yes, you got the 1 plus a half. What did you do here?
I just
Multiply that.
multiplied and I've got the common denominator, but then more.
So you got 1 plus k plus 2. You're actually missing this 1 times a half, so you're missing a half.
So, now that should be plus,
I think I'm going to have to give up on
1, just 1.
It's really annoying me.
Don't give up.
It's really annoying. I don't know where
Let's
I
make
am.
some more progress.
Yes, that's plus 1.
I don't know which side I was working on, to be honest.
2 plus 3 over 4.
Yeah, 1 plus k over 2. Careful with the brackets. This is 1 plus k over 2, all of them multiplied by that.
That's what I meant.
That's one now, okay.
I've done it.
I don't know. Have I done it?
Yeah, okay, yeah, this is what we're looking for. I'll
Okay.
put this on the screen.
There's lots of scribbles. Should I put the light?
You're already very close to it there, Ryan.
It's much better than anyone else.
Scribbles made you wrote something.
Yeah, because I did it several times and then read it several times.
That is true.
There's a few scribbles.
Okay, there you go.
Much more legible than mine.
So the base case, okay, everybody saw the base case is true. You make the assumption, then you're facing this. You factorize it. That allows you to use the assumption here. So you replace this bit by 1 plus k over 2, and this makes it greater than or equal to. Here, this is 3 over 2. So you skip. I think you're skipping that. Okay, so she's keeping the 1 and the half separate and the 1 and the k over 2 separate. Multiply this out symbolically, if you like, without collapsing the 1 and a half. It just keeps it nicer. So you get 1 plus k over 2, 1 times k over 2, plus a half times 1, plus k over 4. And then at this kind of point, you got to keep your eye on the destination you're going to. The destination is this, 1 plus k plus 1 over 2. We've gotten to here. You collapse these two together. K plus 2 plus a half is k plus 1 over 2. So you've got exactly what you want. But annoyingly, there's still the k over 4. And how long did it take you to realize you could just forget about the k over 4? Did that take a while?
It took me ages to get it in that format because
Okay.
I kept doing 3 over 2k instead of 3 over 4.
So one group of people over here had got it to this stage, and then they were staring at this, oh, this bad k over 4. We don't want it there.
No.
But you're allowed to just get, you're allowed to drop it because the k over 4 is positive. Because the k is positive. So k over 4 is positive. So you're allowed to drop it, and that means that this thing is bigger than the remainder. But that's okay because bigger than is still compatible with the inequality you're trying to establish. Yeah? Does that make sense? So that's it, bar the shouting at the end. You know, by the principle of induction, it's true for all k. Yeah? That's good?
Well, I wasn't sure it was right, so I didn't want to write that.
That's correct. Can you see that, Marion? Yeah?
Yeah.
Yeah.
Yeah.